Assalamualaikum and hi everyone. Today we will present our Algebra linear assignment from group 21. So first, I will introduce our group members. First, me myself, Nur Marsha Bilqis. Secondly, Nelly Shafia. Third, Nur Shahida. Fourth, Quratun Aini Iziani. And lastly, Muhammad Shafiq Danish. Okay, so this is our 9-diagonal symmetric matrix that we choose, which is A equals to 7, -2, 0, -2, 6, -2, 0, -2, and 5. For our first question, obtain the eigenvalue and eigenvectors of A. To obtain the eigenvalue of A, we will use the characteristic of equation, which is determinant of A minus lambda I equals to 0. Then we substitute the value into the equation and solve the determinant of this matrix. To solve the determinant of this matrix, we use cofactor expansion on first row. So we get lambda power of 3 minus 18 lambda squared plus 99 lambda minus 162 equals to 0. Okay, then we have to factorize this equation. So first, we find the divisor of 162, which we get plus minus 1, plus minus 2, and plus minus 3. So when we substitute each value, we can see that lambda equals to 3. The result is equals to 0. So we can conclude that lambda minus 3 is one of the factor of the equation. When we get the lambda minus 3 is one of the factor, we have to find another factor of this equation. So, we use long division to find the another factor. And we get lambda minus 6 and lambda minus 9. So, we can see that lambda is equals to 6 and lambda equals to 9. Okay, so we obtain that the characteristic equation is lambda minus 3 times lambda minus 6 and lambda minus 9. And we obtain that the eigenvalues is lambda 1 equals to 3, lambda 2 equals to 6, and lambda 3 equals to 9. Next, to find the eigenvectors, use A minus lambda I times vector x equals to 0 vector. So we change the equation into the augmented matrix form. And for lambda 1 equals to 3, we substitute 3 into this matrix and we get this. So we solve this until we get the matrix in RREF form. So as we can see, the leading variable is x1 and x2 and free variable is x3. So since free variable is x3, we let x3 equals to s, which s is the element of R. And from this matrix, we can see that the first equation is x1 minus 1 over 2 x2 equals to 0, and x2 minus x3 equals to 0. And we get x1 equals to 1 over 2s, and x2 we got equals to s. So the solution space is 1 over 2s, s, and s. And we factorize s and we get 1 over 2, 1, and 1. So the eigenvector for lambda equals to 3 is s, 1 over 2, 1, and 1. Next, for lambda equals to 6, we change it to augmented matrix form and we solve this matrix into RREF form. And then we can find the leading variable is x1 and x2 and free variable is x3. So we let x3 equals to s, which s is the element of R. And from this matrix, we get that first equation is x1 minus 2x2 equals to 0 and x2 plus 1 over 2 x3 equals to 0. So we get x1 is equals to negative s and x2 is equals to negative 1 over 2s. So the solution space is negative s, negative 1 over 2s, and s. So we get the eigenvector is -1, -1/2, and 1. So for the lambda 3 equals to 9, we substitute the lambda 3 equals to 9 into the augmented matrix form. And then we solve the matrix until we get the RREF form. And then we can see that the leading variable is x1 and x2, and the free variable is x3. So we can let x3 equals to s, which s is the element of R. And from this matrix, we also can see that the first equation is x1 plus x2 equals to 0, and x2 plus 2x3 equals to 0. So we get x1 equals to 2s and x2 equals to -2s. So the solution space is 2s, -2s, and s. So we get the eigenvector for lambda 3 equals to 9 is 2, -2, and 1. So to conclude, for the matrix A, we get the eigenvalues is lambda 1 equals to 3, lambda 2 equals to 6, lambda 3 equals to 9. And the eigenvector is 1/2, 1, 1, -1, -1/2, 2, -2, and 1. For question 2, use P that diagonalizes A to calculate A power of 21. P that diagonalizes A can be obtained from the eigenvectors. So P that diagonalizes A is equal to this. Then to obtain A power of 21, we can use formula A power of K equals to P times D power of K times P inverse. So to obtain A power of 21, we can write it as A power of 21 equals to P times D power of 21 times P inverse. Okay, so we already get P. So to obtain D power of 21, we need to put the eigenvalue in the main diagonal form. Our eigenvalue that we obtain is 3, 6, and 9. Then we need to power them to power of 21. Lastly, for P inverse, we can get by this following formula. So first, we find the determinant of P by cofactor expansion on first row. So we get 27/4. And then we find the adjoint P. We know that the transpose of cofactor is equals to adjoint P. So we find the cofactor of matrix first, and we get this, and we transpose this, so we can get the adjoint P. And then we substitute all the formula of P inverse and get the P inverse, which equals to this. After we obtain all of those, we just write it in the form of A power of 21 equals to P times D power of 21 times P inverse. So lastly, we obtain the answer like this.
For question number 3, we need to find the transformation of A which denoted as TA, kernel TA, and range of TA. First, we must find the TA to find the kernel and range, so we need to assume that A is standard matrix of TA. The transformation is from R3 to R3, where R3 indicate the set of all three-dimensional vector. Step 1. We need to multiply the standard matrix with the column vector of X, which also denoted as X1, X2, and X3 in matrix form to find the TA. Then we got 3 by 1 matrix as the result. The first row equals to 7, X1 minus 2, X2. The second row equals to minus 2x1 plus 6x2 minus 2x3, and the third row is minus 2x2 plus 5x3. Step 2. We write down in the form of linear transformation, which is easier to read and understand. We already found our linear transformation, so we can proceed to find kernel and range of TA. Theoretically, we know that the set of vector in V, where V in our case is R3, that map into 0 Labadie, where Labadie is R3, is called the kernel of TA. Therefore, In this case, we suppose that the linear transformation of the A is equal to 0. So, first step, we write it down in the form of x equals to 0 in augmented matrix. Then we perform the arrows until we get the RREF matrix. Therefore, this the solution of the kernel of T is given by x1, x2 and x3 equals to 0. Next, we want to find the range of TA, where we can understand that range is the set of all vectors in Labadie, which is R3, that are imaged on the T of at least the one vector in V which is R3. So, in this case, first step we consider that there are three scalars which are denoted as A, B and C, and they are equals to linear transformation of TA. Then, second step, we perform the augmented matrix form of A equals to scalar vector and find RREF matrix form using arrow same as earlier we write. So, the range of TA is equals to R3.
For question number 4, the question is, assume that P from question 2 is the transformation metric of Tp such that Tp, real number power of 3 mapping to real number power of 3, obtain Tp, curve Tp, and range Tp. In order to know the transformation of P, we need to know what is general linear transformation. If T V mapping to W is a function from a vector space V into a vector space W, then transform T is called a linear transformation from V to W. If for all vectors U and V in V and all scalars C fulfill all the requirements. If V equals to W, then the linear transformation T is called a linear operator on V. So in order to search for transformation V, first we need to search for any vector of X. And here our vector at X is x1, x2, x3. Then in order to search for transformation of P, we are just going to multiply both matrix P and vector X. And hence our transformation P equals to half x1 minus x2 plus 2x3, x1 minus half x2 minus 2x3, x1 plus x2 plus x3. Next, we are going to find the kernel of Tp. What is kernel? Kernel mentioned that if T V map to W is a linear transformation, then the set of vectors in V that P maps into 0 W is called the kernel of T, denoted by curve T. In order to search for curve Tp, first we are going to maps Tp equals to 0 W. Thus, we will get the following of system linear equation. Half x1 minus x2 plus 2x3 equals to 0. x1 minus half x2 minus 2x3 equals to 0. And x1 plus x2 plus x3 equals to 0. Then we are going to do RRAS to this question. First of all, we are going to double the R1 and will become a new matrix. Next, we are going to minus R2 with R1 and minus R3 with R1. Next, we are going to multiply R2 with 2 over 3. And then, we're going to find a new R3 with multiply R3 with R2. And R3 is triple the amount. Next, we're going to find a new R3, which we are going to multiply the current R3 1 over 9. And then we're going to find a new R2 with R2, and the R3 will multiply by 4. And the new R1 is 4R3 minus R1. Next, the last one, we are going to find a new R1. We are going to double the R2 and we'll plus with R1. Therefore, we find out that x1 equals to 0, x2 equals to 0, and x3 equals to 0. So this meaning that the only solution is the trivial solution. Hence, the kernel of Tp is equals to 0. Next, we are going to find the range of Tp. Range mentioned that the set of all vectors in W that are images under T of at least one vector in V is called the range of T, denoted by RT. So Okay, no need to search for range TP. We are going to do RR if F as well. It's the same as the kernel one. And then we found out that the rank of TP is equal to 3. Therefore, range of TP is equals to real number of power of 3.
Question 5 is assume that A is the standard matrix of TA such that TA is the transformation of polynomial P2 to P2. Obtain TA, kernel of TA, and range of TA. So our matrix A is 7, negative 2, 0, negative 2, 6, negative 2, 0, negative 2, and 5. So and it is the standard matrix of TA. So first step is we need to find TA by multiply polynomial that have three elements, which is A0, A1, and A2 with our matrix A just now. So then we get TA is 7 A0 minus 2 A1, negative 2 A0 plus 6 A1, minus 2 A2, and negative 2 A1 plus 5 A2. Next, we changed into the polynomial form, which is 7A0 minus 2A1 plus negative 2A0 plus 6A1 minus 2A2x plus negative 2A1 plus 5A2x power of 2. Then we need to assume the Px equals to 0 vector of polynomial to find the kernel. So we need to compare the left side and the right side, this one and this one, to find the value of A, A1, A0, A1, and A2. Then we do ERO to get the value of A, and from the final answer of the ERO, we get three equation, and we get the value of A0, A1, and A2 is equal to 0. Thus, the kernel of TA is 0 plus 0x plus 0x squared, which is the 0 vector of polynomial P2. Since that, this shows that TA is a one-to-one function. For the range, as we learned in the lecture, range is a set of polynomial in W, which is P2, that image under transformation TA from V at least map from one polynomial set. So first, we need to assume that vector of polynomial P2, which is A, undergo transformation TA and will map to vector of polynomial B, which is also P2. So next, we do the ERO, and from the ERO, we will get the value of A0, A1, and A2 in terms of B. So we get 2 over 109 B0 plus 7 over 109 B1 and plus 19 over 109 B2 for A2, and 123 over 2071 B0 plus 35 over 218 B1 minus 2 over 109 B2 for A1. Next, we have 246 over 14497 B0 plus 5 over 109 B1 minus 2 over 109 B2 for A0. So we found that finally we get the range of TA in terms of B, B0, B1, and B2, and we change in the form of polynomial, and we found that range of TA is equals to P2. Thus, this shows that transformation TA is onto.
For question 6, they ask us to find P prime that orthogonally diagonalize A by using the Gram-Schmidt process. First, we need to know, is our metric A is orthogonally diagonalizable? By theorem 4.7, state that for a square metric A, if A is orthogonally diagonalizable, then A is symmetric. In fact, that the converse of the theorem 4.7 is also true. Thus, A is orthogonally diagonalizable if and only A is symmetric. Here, we can see that our metric A is symmetric. Thus, our metric is orthogonally diagonalizable. Does metric P orthogonally diagonalize A? So, P has to be an orthogonal metric. What is orthogonal metric? Orthogonal metric is a square metric such that its transpose is the same as its inverse. From question 2, we obtain metric P. And here we can see that our P transpose is not the same as the P inverse. Thus, our P is an orthogonally diagonalized A. However, we can find P prime that orthogonally diagonalize A by using Gram-Schmidt process. Here, we let those column vector as the element of R3. The first step is, we need to let the vector V1 equal to U1 equal to 1 over 2, 1, and 1. Then the second step is, we need to find the vector V2 by this formula. So here, we obtain vector V2 is negative 1, negative 1, 2, 1. For step 3, we need to find vector V3 by using this formula. Here we obtain our vector for V3 is 2, negative 2, and 1. Next, we gain the orthogonal basis. Next, we need to normalize vector V1, V2, V3 in order to form an autonomous set in Euclidean space R3. So, we need to find the norm of V1, V2, and V3 by normalize them. Here we got norm V1 equal to 3 over 2, norm V2 equal to 3 over 2, and norm V3 equal to 3. And then we can write it in orthonormal basis. When the norm not equal to 1, we normalize them by the process of multiplying the reciprocal of the norm and the element itself. Then we got our orthonormal basis. Lastly, we write our orthonormal basis in the metric form. And we gain that P prime that orthogonally diagonalize A.
For this question 7, we have two parts, which is the first part is show that P prime from question 6 orthogonally diagonalize A given the Euclidean inner product. So the P prime that we get from the previous question is 1 over 3, negative 2 over 3, 2 over 3, 2 over 3, negative 1 over 3, negative 2 over 3, 2 over 3, 2 over 3, and 1 over 3. So to show that P prime is orthogonally diagonalized A, we need to show that P prime transpose times A times P prime equals to D. D is a diagonal matrix. So we need to times the P prime transpose with the A matrix and P prime. Then after all the working, we get a matrix with element 3, 0, 0, 0, 6, 0, 0, 0, 9. So this shows that the answer from the P prime transpose A P prime is a diagonal matrix. This shows that P prime orthogonally diagonalized A. Second part is, does P prime also orthogonally diagonalize A given the weighted Euclidean inner product? So this is the weighted Euclidean inner product. So first step is we need to divide P prime into three parts by column, which is U1, U2, and U3. Next, we have to find the inner product of each pairs. And we found that the weighted Euclidean inner product of P prime is not equals to 0. Then From that, we can see that P prime with weighted Euclidean in a product is not orthogonally diagonalized A. That's all from us. Thank you.